Let's start chapter number 8, three-phase circuits in power systems. So three-phase circuits are the most commonly typed circuits and systems in the power generation, transmission, and distribution. Why three-phase circuits are commonly used? There are many advantages of three-phase circuits over single-phase circuits or two-phase circuits. And as you can see, some of these advantages are listed right over here. As you will see that three-phase circuits are not much complicated to create, that is the generator to create a three-phase system is not much complicated as compared to a single phase generator that we have discussed. We have discussed DC generators, of course, and we're going to discuss AC generators from this point on. Specifically in chapter number 16, we are going to discuss AC synchronous generator. But as far as generator construction is concerned, the construction of a single phase generator and three phase generator are pretty much similar, except the armature where you have the winding, or if the winding is on a stator, then of course the stator. So the first important quality of three-phase system is, as I mentioned, they're not much complicated as compared to the single-phase system, and they turn out to be cheaper and more efficient in terms of the power delivery, power generation, and power delivery. They can deliver more power for a given weight and cost of the line, and the voltage regulation, that is the voltage from no load to full load, it is much better for three-phase transmission line as compared to a single-phase transmission line. Now, in America, we have only a single phase out of the three-phase system coming to our homes. So all of our homes, basically, we are equipped with 110 volt RMS 60 hertz system. For most of our appliances, most of our sockets, we also get 220 volt for the appliances that require that are heavy in load, that require more current. But even those 220 volt, it is still coming from a single phase, as you will see shortly. Now overseas, you have all three phases. In many countries, you have all three phases coming to your home, and in your home you have different parts of your home assigned to different phases. So for example, if in some country, which is very common in some other countries, power outages, if one phase goes down, then you can always put the load that is on that phase, you can always put that load on another phase, and then you can get power throughout your home. But as I said, in America, we have only one phase coming out of the three phases. So how is the one phase coming out of the three phases? With an arrangement like this. So this is a transformer. Your main step down voltage is coming to the primary side of the transformer. Again, we're going to discuss transformer in the next chapter, but this is a center tap transformer. This is the primary side where your main line is connected, and main line voltage, as it is shown over here, let's say is 2.4 kilovolt. Now on the secondary side, you have the winding divided into two parts exactly in the center, and that's why it's called center tapped. Again, in the next chapter we will study how does a transformer work, but basically it works based on Faraday's law of electromagnetic induction. You send an electrical AC voltage and AC current in the primary side, this side, and then this creates a flux, which is sinusoidal flux, changing with respect to time, and that flux links with the secondary coil, hence inducing a voltage in that, because the flux is changing with respect to time. And once the voltage is induced in it, of course, once you connect the load, then the current will start flowing from that induced voltage, and your load can consume power. So this is a center tap type of transformer, that is the winding is divided in half, and each of these two halves, basically the way they do the winding and the number of turns that they have, it is stepping down the voltage from 2.4 volt, basically from this point to this point, from the top to bottom, it is dividing it by 10. So 2.4 kilovolt to 240 volt. 2400 volt to 240 volt from between the two top and bottom terminals. And between each of the top and the center and bottom and the center, you have 120 volt voltage, but they are out of phase. So the voltage over here is going to be going like this, and the voltage here is going to be going like this, with peak value of 120 volt times square root of 2, right? This 120 volt is RMS value. So when you add the voltage from top to bottom between the two lines, it will add up to 240 volt, right? This, let's say the top value, if you add 120 volt RMS minus negative 120 volt RMS, is going to give you 240 volt RMS value. Of course, this is not RMS, this is peak to peak. So whatever the corresponding peak value is going to be, the RMS will be derived from that by dividing the peak value by square root of 2. So your heavy load basically is connected to the two ends, and it is getting 240 volt. And your regular sockets are between neutral, which is the center point, and the lifeline between 120 volt and the neutral. Now in three-phase system, you have three different voltages, and these voltages are isolated from each other. Each of the voltage, if you draw the phasor diagram, each of the voltage, if I draw the phasor, you have like this. This is your phase A, we call it VAN. N is the neutral, as we're going to discuss soon. This is phase B, VBN, and this is phase C, VCN, as you can see over here as well, right? Now each of these phases are 120 degrees apart from each other. So the phase difference between each of the phases is 120 degrees. VAN leads VBN by 120 degrees, and VBN leads VCN by 120 degrees. Good. And this is the sinusoidal voltage of the three phases. Phase A is blue, phase B is red, and phase C is green. So let's look at how the generator differs from single phase to two phase to three phase generator. Okay, single phase generator is basically the same way we discussed our DC generator. Remember, if you don't put commutator in the DC generator, the natural waveform that it is going to give you is a sinusoidal or an AC waveform with the slip rings. Remember, we basically remove the slip rings, and then we put commutator to convert the AC into DC. But if you have the basic generator with the slip rings, that's going to give you an AC waveform. So observe this. Now here our magnet is moving, our armature winding are static. The generators that we discussed earlier, our armature was moving, that is the windings were moving, and the magnet was static. Here in most of the AC generator, especially the one that produce high power, high current, high voltage, you don't put a moving armature. Why? Because of course in the moving armature you have to put brushes, and then when the high voltage, high current is coming out, there will be drop at the brushes, and you will lose power. The brush life is going to be less, and you don't want the high voltage, high current part to be moving. So in general, we have a DC magnet which is moving, which can be either permanent magnet or electromagnet, but that's a DC magnet that is moving, and you put the windings in which the voltage is induced in the static part of the generator. Though this is called stator and this is called rotor. So as you see, your magnet is moving in the clockwise direction. You have one set of winding, A and 1. So it's a winding that goes from the back and makes a turn. And as we discussed, when the flux is going to be linked with that, you're going to have the maximum voltage induced in it. When let's assume flux is not linking with it, when it turns 90 degrees, then of course there is no voltage induced in the winding. Now when you are observing, remember the induced voltage equation that we observed, L dot V cross B. In this, V was the velocity of the armature, that is velocity of the winding. Here the windings are static and magnet is moving. So this V will be considered as the relative velocity over here. That is velocity of the winding with respect to the magnet, and the direction will also be with respect to the magnet. So if magnet is moving clockwise, winding with respect to the magnet will be moving counterclockwise. I mean, it's not moving, but let's say if you sit on this magnet and look at the winding, it will look like that the winding is going in the opposite direction as you're moving in clockwise. It's gonna go in the opposite direction. So this velocity is the relative velocity with respect to the magnet. So again, if at this point the velocity of the magnet is towards J, then the velocity of the winding or the armature is going to be negative J, and that's what we are going to take over here for the velocity when we are calculating the induced voltage. The velocity in the direction of B, of course, based on north and south, is gonna be this direction, negative K. So you can calculate the induced voltage, whatever induced voltage is going to be, and again I'm calculating it here, you can understand it. So you're gonna get a single phase, a sinusoidal voltage, of course, based on the position of your magnet. As we discussed for the DC case as well, it's the same thing, except the orientation or the configuration of the generator is opposite, winding on the static part and magnet is moving. So that's the output of a single phase AC generator. And remember, the only thing that is different again is the relative velocity concept over here. The power, single phase power, is RMS value of voltage, RMS value of current. RMS value of voltage is, for the sinusoidal waveform, is the peak value over square root of 2. So that's going to be peak value over square root of 2. RMS value of current is the peak value over square root of 2. So the total power is V peak I peak over 2, which you can see over here. And the active power, the unit is watt, as we studied in the last chapter. Now from the single phase generator to two phase generator. Alright, observe same type of configuration. The only difference is we made arrangement in the static part, in the stator, to insert one more set of winding which is not connected to the first set. So they are isolated from each other, right? So now the voltage will be induced in B2 set of winding and A1 set of winding separately. So when this magnet is moving, at this time, let's say A1 will have the maximum voltage induced, which is right here, and B2 has 0 voltage induced, which is right here. As it will move 90 degrees, that is, it will be towards B2, then the winding B will have the maximum voltage induced, and winding A will have the minimum or 0 voltage induced. And then this this will keep on going. So now you have two sets of voltages, and both voltages are what, 90 degrees apart from each other. As you can see, they are 90 degrees electrically, 90 degrees apart from each other. Their equation can be given by EA is Vp cosine omega t, and EB Vp cosine omega t minus 90 degree, right? EB is following EA by 90 degrees, or it is 90 degrees lagging EA by 90 degrees. Okay, how are you going to calculate the total power? Similarly, each phase is going to get Vrms, Irms. So since there are two phases, you add both power of both phases. So the total power of the system will be 2 Vrms, Irms, or V peak, I peak. So now, just making a small arrangement in the same generator. Remember, the motor rotation speed is not changed. Your magnet is the same. The power that you are giving to rotate the magnet is the same, which can be, any source, any turbine. And just by doing an extra arrangement of winding, you start getting double the amount of power as compared to single phase. So let's go to three-phase system. Same concept. Okay, make sure you follow the example 8.1. It's example 8.1. We are saying that you have a two-phase generator, it is running at 6000 RPM, RMS voltage generated is 110 per phase. So it is asking you what is the peak voltage per phase. So since RMS is given, a square root of 2 times RMS is the peak voltage. Output frequency in hertz, since RPM is given to you 6000 RPM. Remember, hertz is what? RPS, rotation per second. So all you have to do is to do 6000 rotation per second. So you change minute into second. 1 minute is 60 seconds. So that's going to give you 100 hertz or 100 rotation per second, which is right here. And then time interval between the peak of two phases. Two phases are separate from each other by 90 degrees, remember. So the time period of one waveform is 10 millisecond because the frequency is 100 hertz. And phase difference between the two peaks is 90 degrees, which is 1/4 of the full cycle, complete cycle. So you go 1/4 of the time period, which is 2.5 milliseconds. So that's the difference between the two phases. Now, three-phase generators, observe same arrangement. Same arrangement, again, the only difference is now you are introducing the third set of windings. And electrically, each set is going to be 120 degrees apart from each other, as you know I mentioned at the beginning. So same thing is going to happen. You don't have any difference in the power, in the mechanical power that is being input to the generator, because your turbine is the same, and from the same mechanical power you're getting more electrical power just because you introduce one more set of winding, right? So a lot more efficient as far as power output is concerned. You have three waveforms, one waveform for each set of windings, and each of the waveform, each of the phase is 120 degrees apart from each other. And the equation, the time domain equations for each phase: V peak cosine omega t for phase A, V peak cosine omega t minus 120 for phase B, it's lagging phase A by 120 degrees, and phase C, V peak cosine omega t minus 240, which we can also write cosine omega t plus 120 degrees if we go counterclockwise instead of clockwise. And the total active power or average power is 3 times the single phase power, 3 times Vrms Irms, or 3 by 2, 1.5 times V peak I peak. So in the next video we're going to look at how to represent the circuit of a three-phase system.